In this chapter, we're going to review some topics in algebra that will help prepare us for the calculus course that's coming up. In this lesson, we're going to practice finding the domain of a function.
So right now what we're going to do, just like we said there, we're going to find the domain of some different functions here. The concept of domain, looking for the domain of a function, this is really important for identifying like when you have a solution to a problem. When you look at an equation or an expression here, is there anywhere any values of the independent variable that simply don't work? And it's important to recognize that, and you'll see applications of that in all sorts of different places here. So let's just run through a handful of problems here. So we're just going to find the domain of the following. And so I'll just throw down some examples here. So the first one, let's say, is the square root of 3x plus 4. Now, I want to start with this one right here because it's the radical function is an important one. And not only that, but it's one that tends to lead to some confusion here. For a couple of different reasons. First of all, we all know that you can't take the square root of a negative. Well, the truth is, yes, you can. You can take the square root of a negative. It's just that the result that you're going to get isn't real. So when I ask for the domain of the following, bear in mind I'm talking about real numbers. I'm trying to push you in that direction there. Now, in addition to that, there tends to be this assumption that if you can't take the square root of the negative, well, it must be the case you can't take the square root of 0. And that's also a mistake. Yes, you can take the square root of 0. Just think about it. What's the square root of 0? 0. So when we take a look at this, under the radical symbol here, for us to figure out the domain in real numbers, what we need to do here is we need to impose upon this expression here the relation here that it's got to be greater than or equal to 0, because I can have it or equal to 0. So now what I'm going to do here is I'm just going to isolate the x in this inequality. First thing I'll do is move the 4 over. Now there's no problem moving an object from one side to the other of an inequality. The only time you've got to worry about changing the signs is if you're ever multiplying or dividing by a negative. That's the only time that causes problems. So right now I'm going to divide by that 3. And that isn't going to cause me any problems whatsoever. The answer here is going to be x is greater than or equal to negative 4/3. Now, another way you might write this, okay, you might write this as negative 4/3 out to infinity if you're going to use interval notation. And I hope you've seen interval notation before. We're gonna bump into it over and over again in this course. It is something that the assumption is at this point that you know the relationship between these two ways of expressing that answer there. Hopefully you do. We should have plenty of time to practice that over the next lesson or two here. Let's take a look at another one here. B. Let's do this one here. Let's just throw something straightforward like this. 1/5 x cubed plus 2x squared minus 7, let's say. Okay, so let's really talk really quickly about this one right here. What is this? Well, if you were to give a name to it, you'd call it a polynomial, okay? Cubic term, quadratic term, got a constant term here. Polynomials are notoriously wonderful to work with because they're so smooth, they are continuous. There's no point where there's a hole or a gap in them. They're just wonderful functions to work with here. There is no number out there that you cannot cube and then square, multiply by the two values and add together. There's nothing wrong with this right here. There's nowhere where this would lead to a problem. So our domain, the best way to write that is simply to say that x, okay, those x's right there are both elements of the real numbers. Doesn't matter what real number you pick. You can pick any number out of the real numbers that'll work. So it's all real values there. That's the nice thing about polynomials. They just work out so wonderfully. I tell you what, let's go back to the radical here because that's an important one here. Take a look at x squared. We're going to take the square root of x squared minus 4. Now I need, in this case here, what's under the radical symbol to be greater than or equal to 0. Now in the first question here, I had a little linear that I had to make greater than or equal to 0. Now it was very easy for me to work with because I just move over one term at a time and then divided by the coefficient, away we go, we're done. It's a little bit different when you've got a quadratic there or anything higher than that. So this is a slightly different sort of a problem. So here's what we're going to do here. This is how I would advise people to go about approaching this problem. I need to figure out where this thing is greater than or equal to 0. Now, there are a couple of ways that I can do this. Okay, and I will show you a couple here. But for right now, what I would do with this is I would treat this as if it's a parabola. I'm going to go back to what you would have looked at earlier on. And let's just take a look at this as if it's a parabola here. Let's figure out where the parabola goes to 0. So if I take and split that up into its two factors here, x minus 2x plus 2, I can see right now that this parabola here is going to cross the x-axis at a value of -2 and a value of +2. Those would be the x-intercepts. Now just ignore the greater than or equal to 0. That's not an issue right now. I just want to know what this looks like. This is my parabola here. I want to know where this thing is greater than or equal to 0. So what does it look like here? Well, it's got roots at -2 and 2, and it opens up. I know that it opens up because the leading coefficient here is positive. And in fact, in this particular case here, if it was negative, I would simply move everything over to the other side of the equation so that it was positive, because I want it to open up here. Now, this little drawing that I've given you right here, representative of the coordinate plane, because you'd have your y-axis right here. I want to know where this function is greater than or equal to 0. Now, bear in mind what I'm asking here. Remember that if I was to graph this, or if I was to show the equation of this, I would say y is equal to x squared minus 4. That x squared minus 4 right here is equivalent to y. This is y. So when I ask this question right here, I am really asking, okay, this question right here is asking, where is y greater than or equal to 0? So on this function here, where are the y coordinates greater than 0? Like if you pick a point right here, is its y coordinate greater than 0? Yes. Here? Yes. Here? Well, it's equal to 0, so that still counts, yes. But down here, no. None of the points between -2 and 2 have y coordinates greater than 0. Then back out here on the other side of 2, yes we are. All of a sudden the y coordinates are all, once again, greater than 0. So where is this function greater than or equal to 0? Okay, when x, okay, and when I move to the other side of -2, when my x coordinates are to the other side of -2, then that pushes my y coordinates up. So when x is less than or equal to -2, and where x is greater than or equal to +2. Okay? Now, another way to write that might be to say from -infinity up to -2, and I use my bracket here to indicate or equal to. And then I'm going to use the union symbol because it looks cool, and it means together with the interval from 2 out to +infinity. Okay? And that will be the domain of this particular function here. Now, there's another way we could have done that. Okay, we could have gone back over here and just simply said, okay, x squared minus 4, I need that to be greater than or equal to 0, which would mean x squared has got to be greater than or equal to 4. Like I can do this a little bit more algebraically here, but there's a bit of a trade-off here. This method, taking a look at what the graph of that function looks like, okay, and then pulling out the necessary piece that I need from there, that's actually, I think, fairly clear conceptually what's going on. Doing this a little bit algebraically might not be quite as obvious, because at this point in time here, I'm going to take the square root of both sides. But when I do that, okay, what happens here is, as soon as you take the square root of that 4, you're going to run into a problem, because the square root of 4 is not just 2, it's plus or minus 2. Sorry, the solution to this, sorry, I said that wrong. The square root of 4 is 2. But the answer to this, if x squared is equal to 4, then x could be positive or -2. Okay? And so what I need this to be here is I need the absolute value of x to be larger than, greater than or equal to 2 in order for that to work. Okay? I mean, because either that value of x is going to be less than -2, or it's going to be greater than +2. And so So to go from here to here, when you take that square root with that inequality there, I got to pay attention to what happens with the signs that pop up, right? That positive or negative there. And the best way to do that is simply say, okay, if you take the absolute value of x, that number will be bigger than 2. And again, that means right there the same thing as what I've written over here. That means we're talking about values of x that will be less than -2 up to -2, or from 2 out to infinity. Okay, but you'd have to be comfortable enough to know that there's a connection there. Okay, I'm sorry, that was a long explanation for that one, but there was a fair bit going on there. Let's take a look at another one here. Let's take a look at something. Let's back off a little bit, make it nice and straightforward here. What if you had just a simple little rational like that? And I think this one here is a lot simpler than the previous one because we know that you cannot divide by 0. Okay? So I cannot allow 3 minus x cannot be equal to 0. Okay, that just can't happen. So now I will solve that inequality. I'll move the x over, and we'll get in very short order that x cannot equal 3. That's it. That's all you got to do. Let's do another one here. Let's say, okay, I tell you what, let's combine a couple of these together. Let's say 1 over the square root of x plus 6. I'll make the radical here a little bit easier. Sorry. Now, taking a look inside the radical there, just like we did before here, you would take a look at this and say, oh, okay, if all I was considering is the radical here, then I know that x plus 6 has to be greater than or equal to 0. Now, some of you are going to probably react to that immediately, and rightly so, because what I've written there is wrong, but this is a good place to start. When you look at the radical, I know that what's underneath the radical has to be greater than or equal to 0. But because this is in the denominator, I can't include the 0, right? Because if this term here goes to 0, the square root of 0 is 0, but then I'm dividing by a 0, and I can't allow that. So there's an added restriction here that x plus 6 must be greater than 0. Okay, I don't have the option of being or equal to 0, and if I move now to isolate the x in the inequality, I'll get that x is larger than -6. And that's the domain restriction I'm looking at. Okay, let's just do one more here. I'm just going to pull out another question, another type of function here that we might bump into. Let's say that we had, I don't know, let's say the negative, and here we go, absolute value of x minus 4 over 6. In other words, we just want to take a quick look at what happens with an absolute value here. And the truth is, taking the absolute value of a number doesn't cause any kind of problems here. You can take the absolute value of any value of x. There is no value that I can plug into there that will cause me problems. You just take the absolute value of everything. So as a result, in a case like this, we might just say that the domain is all reals. Okay, so that's just a little bit of a kind of a review of some of these ideas that you've looked at before. Again, being able to look at a problem and identifying issues in the domain really sets you up for success later on in a problem.
Now we'll review solving equations.
Okay, now in a minute we're going to get back to looking at intervals and looking for essentially domain. The domain of a function where it's either positive or negative sort of thing. We're going to break that up because it's an important idea in calculus for sure. But the last lesson that we were working on, we were looking at factoring, and just earlier in this particular lesson we were looking at issues of domain. So what I want to do right now is just take a few minutes and kind of put together a couple of these ideas and talk about solving. We're going to solve some equations here. Now I'm going to start off with some pretty straightforward ones here, and then they'll get a little bit more complicated, but we're not going to go very deep into this because it's not really necessary in this course. Okay, so you'll see. Okay, so let's take a look at, well here, let's just start with some pretty straightforward ones, mostly just to remind you of how this works. So let's say we've got the equation 3x squared plus 9x minus 30 is equal to 0. And I want to solve this. Well, it's a basic quadratic. A quadratic is a polynomial. The domain of a polynomial is going to be all reals. Okay, so basically everything's a possibility here. To solve this, I have to factor. I got to use a skill that we've been practicing earlier here. But I'm lazy. I'm so lazy. I notice that every number here is a multiple of 3, so I'm going to divide both sides of the equation by 3 to get x squared plus 3x minus 10 is equal to 0. Okay? So now, although I've changed the equation slightly, I haven't changed the solution, and that's important to remember. I am changing the equation, just not the solution. And now I'm going to factor that, break it apart into its constituent factors here. This will be x and x. Now I'm looking for factors of negative 10, whose sum is going to be 3. Because it's positive 3, the larger number's got to be the positive one, so obviously I go to 5 and 2. That's kind of my go-to there. And I recognize from here that if that's the factored form, my solutions would then have to be negative 5 and positive 2 to make those work. Okay, and now because those are both real numbers and we knew that the domain was all reals, that works. Nothing wrong with that at all. And let's take a look at another one. Let's say that I give you the equation 4x cubed, let's say plus 3x squared, and that's equal to 16x plus 12. All right, so I got a cubic here. And it's on both sides of the equation here, but when I get a polynomial like that, and I know it's a polynomial, there's no radicals in here, there's no rationals, I'm going to bring everything over to one side of the equation first so that it's equal to 0. Okay? Now, I hope you understand that you have to do it this way. Okay? I've watched students try to do this by canceling an x and setting x equal to something with an x over here and thinking that they're getting the solution, and they really aren't. Okay, the most direct way to do this, if you've got a polynomial, is to bring everything over, factor, and then take each factor and set it equal to 0. A lot of people try to solve these things as if they're linears. Like with a linear function, yeah, you can just bring stuff over, then divide it out, you get your answer real quick here. But if it's anything greater than a linear, no, it doesn't work out like that. You've really got to do it this way. Now, this particular question right here, it's got 4 terms in it, and I've seen a couple of different ways of doing this, but I should always check grouping first. Okay? And again, I know we've said this before here, but with grouping here, I see that there's this negative 16. I am going to put a positive sign here, and I'm going to move that negative over with those 2 terms. I do that because if I don't, I may inadvertently factor out a negative, and I don't want to do that too soon because I'm going to do that wrong probably. Okay, so what I mean by that is if I put that parenthesis between the negative and the 16, and then I factored it out of here, but I didn't factor it out of here, and that's a mistake. I either do it with both terms or neither. And so I start off with doing it to neither. Now, I look at these 2 terms here, what's common? And there is a common x squared. Okay, and when I pull that out, I will get 4x plus 3. And then over here, between those 2, there is a common factor of negative, and now I'll take it out because now I am confident that I will take it out of both properly. There's a common factor of 4 there, and that will leave me with 4x plus 3. And I know that I'm on the right track here because I can see a 4x plus 3 and a 4x plus 3 here. So now I will take out the common 4x plus 3. I'm left with x squared minus 4. And I know that x squared minus 4 can then be factored one step further, and I'll get 4x plus 3, x minus 2, x plus 2, all equal to 0. So everything's been equal to 0 since I moved it over on that first step there. Now I've got a bunch of linear factors multiplied together. 4x plus 3 will become 0 if x is equal to negative 3/4. X minus 2 will go to 0 if x is equal to positive 2. And x plus 2 will become 0 if x is equal to negative 2. And so those are my 3 solutions. There were no restrictions on the variable up here, so those are my solutions. Okay, now let's take a look at another one here. Let's try this one. 2x squared minus 10 is equal to 0. Okay, now a couple of ways I can do this one. I see that this is a polynomial function right here. So it's set equal to 0, so I'm probably going to just factor that out first. I take out the common 2, or actually, you know what? I don't know why I'm taking out the common 2. I can just divide both terms by 2. So x squared minus 5 is equal to 0. All right, now, because x only shows up once in this expression, I could actually do something, I could do two different things here. I could, for example, factor this, and you might look at that and say, oh, that doesn't factor. I can force it. I can make this x minus root 5, x plus root 5, okay, and force that to have the look of a difference of squares, in which case my solution would be, well, in this case here, for this term to go to 0, x would have to be positive root 5. For this to go to 0, x would have to be negative root 5. Okay? Or with x squared minus 5 equals 0, what I could do is simply bring that 5 over, which is probably what a lot of you would have done here. Now, the only issue when you do this here is you're going to have to take the square root of both sides. Okay, well, the square root of 5 is just root 5. But bear in mind here, because I was squaring the x, whether the x was positive or negative, the result would have been a positive. So I don't know which of those two was intended, so I have to include the plus or minus there. So just please make sure that you remember to do that. Okay, let's look at another one here, D. What's the next one I got here? I've got an x cubed plus 4x squared plus x minus 6 is equal to 0. All right, good. Now, I got 4 terms here. They're all on one side set equal to 0. This is a polynomial. The domain of the polynomial is going to be all real, so I'm good to go. I would love to group this, but I can see right now that that's not going to do anything for me, because if I put parentheses around these two, I can take out a common x squared. That's going to leave me with x plus 4. Here, I am not left with anything that's common like that, because I got an x minus 6, and that's it. There's nothing to take out, and that's not the same as x plus 4. Grouping doesn't work. So now I got to use the integral 0 theorem, okay? And I know that my possible factors here will be x plus or minus 1, x plus or minus 2, x plus or minus 3, whoops, off the screen, x plus or minus 6. These are my possibilities. So now I will check to start off with. Let's say I'm going to check x minus 1. Now, with x minus 1, I will pop in there positive 1. So 1 cubed plus 4 times 1 plus 1 minus 6. Let's see what this equals. Well, 1 plus 4 is 5 plus 1 is 6. Well, there it is, 0. So right now I know x minus 1 is a possible factor. And I can already see that positive 1 is a solution. That's one of them. So good. Now, instead of checking all of those things in there, because I don't know, I might end up with a quadratic root in there or something, I'm just going to I'm going to divide that out. So I'm going to put a 1 out here. I'm going to use synthetic division. So 1, 4, 1, negative 6. Those are my coefficients. Okay, and now I'm going to bring down the 1, multiply, and then add. Multiply and then add, multiply and then add. And I get a 0 down here, and that's fine because that's the remainder, and I knew that was supposed to be 6. So we've gone over synthetic division in an earlier lesson here, so now we're just utilizing that tool. So what this tells me now is that that expression that I was trying to solve could actually be rewritten as x minus 1, okay, multiplied by x squared plus 5x plus 6. X squared plus 5x plus 6. That result will equal 0. Now I am hoping that this quadratic is relatively easy to factor, and it is in fact. Oops. Because if it wasn't, then I'm not stuck. Because even if it's hard to factor, I can still use the quadratic formula and that'll work. But now I factored that down, okay? I can now find the root from each of these little linear factors. So with x minus 1, I know that x could be 1. X plus 2, x could be negative 2. X plus 3, x would be negative 3. And so there's my 3 roots. 1, negative 2, and negative 3. Awesome. All right, let's take a look at a slightly different form. Just keep on trucking here. X to the 4th minus 5x squared plus 4 is equal to 0. Now, I'm only bringing this one up here because of how it ends. Okay? there are two levels to this question. It's a quartic, but it's got the structure of a quadratic. We've talked about that in an earlier lesson here. So I don't quite know how to deal with this. So what I'm going to do is I'm going to change the structure of this question. I'm going to introduce the variable a, and I'm going to let a be equal to x squared. And again, and I've shown you the benefit of that earlier on. But if I let a be x squared, then x to the fourth can actually be rewritten as a squared. Now just think about that. If a is x squared, then this becomes x squared squared. There it is, x to the fourth. Minus 5, oops, sorry, I am trying to change the variable here. 5a plus 4 is equal to 0. Now, I can factor that, or at least I can try to. If I can't, I can always use the quadratic formula. But factors of 4 that can be combined to get negative 5, well, they both have to be the same sign. And if this is negative, they're both negative. So negative 4, negative 1. There we go. Now I have to go and apply well, actually, no, there's a couple ways to do this. You know what, I might even solve this right now. I'll show you how that would work here. Here, I know that a would either be 4 or a would be equal to positive 1. Sorry, I was going to write negative, but I meant positive 1. And then what I can do now is say, okay, but this is actually x squared is equal to 4, or x squared is equal to 1. That's what I just found out here. And when I take the square root, I simply need to remember the positive or negative for both of those. So positive or negative 2, positive or negative 1. Okay? And so that's the secondary part that I wanted to talk about here, was that inside level of mathematics where there's that quadratic. Now the other way that this could have happened was we could have rewritten this as x squared minus 4 and then x squared minus 1 equal to 0. And then notice that these were both difference of squares. Okay? And then same sort of thing. Each one of those linear factors, we would then pull out the solution. 2, negative 2, positive 1, negative 1. We're getting the same set of solutions here. All right, now let's change gears a little bit here. Let's take a quick look at a rational. Let's say you've got x minus 3 over x plus 4 minus x plus 2 over x minus 5 is equal to 0. Okay, now for me to solve this, there are a couple of different ways that I can do this, but they both end up doing the exact same thing, just in different places, I guess is the best way to describe it here. Like I could move that second term to the other side and then cross multiply here, but the other thing that I could do here is I could multiply the entire equation through by the common denominator, by the lowest common denominator here. Now in this case here, okay, bear in mind when I say common denominator, I'm referring to factors. I know that there's an x here in the denominator, there's an x here in the denominator. That does not make x common. Okay? Because when I'm talking about common, when we say that in this context, we're talking about factors here. X is not a factor. X is an addend in there. So I've got a factor here, I got a factor here. Okay, it's like 1 over x plus 4, 1 over x minus 5. If that word factor is kind of throwing you off there, that's what I mean by that. So I can multiply this whole thing by x plus 4, x minus 5. Okay? And when I do that, when I multiply this first term, the x plus 4's will cancel. I will be left with x minus 3 multiplied by x minus 5. Minus, and then in the second one, the x minus 5's will cancel out, and I'm left with x plus 2, x plus 4. On the right-hand side of the equation, because it was a 0 there, if I multiply this all out by 0, you get 0. Now, I have significantly changed the equation. But it turns out multiplying both sides of the equation, although it will change the equation, doesn't change the solution. I do, however, have to state one thing, because I've gotten rid of what is visibly a non-permissible. I could tell right from the beginning that my domain was x cannot equal negative 4 or positive 5. But as soon as I multiply through by this product of binomials here, I've lost that visible restriction. So I need to include out back here, hey, look, x can't equal -4 or +5. Okay, that restriction is now visibly gone, but it was there in the problem, so I need to write it out again so I don't lose it. Now what I'm going to do is I'm going to multiply out everything, expand it all out, and then I'll piece this thing together and start to solve. So this will be x squared, what do we got here, -8x plus 15. Now I'm going to multiply this out, but bear in mind I'm subtracting it as well. So this will be -x squared minus 6x minus 8 is equal to 0. Okay, again, understanding that x can't be -4 or +5. Now someone's going to ask, oh my gosh, do I have to keep writing that out every single time? Well, you tell me, are you going to remember that that's there or not? I mean, I've watched students that have done this, stopped writing it, and then forgot about it. And then they made a mistake in their answer because they forgot that that was there. So it's totally up to you. Now here though, be aware that x squareds will cancel. I'm going to get -8x minus 6x. I'll just write this over here because we don't need a lot more space now. That'll be -14x. Okay, that's that -8 and the -6. And now for the constants here, 15 minus 8 is going to be 7, +7. Okay, now I don't have room to write out my restrictions there. I do, however, realize that they are there. I might bring the 14x over, so 7 is equal to 14x. And then when I divide, 7 over 14 is the same as a half. So there's my solution here. Now, I got to compare that to the restriction that I found. X can't be -4, x can't be 5. Okay, that's okay because the answer that I got was a half. So that's fine. I'm good. Let's take a look at, let's say, one more question here. It's maybe just a tad more difficult than that one. Sorry, which letter did I get to there? I can't remember. E, F, G. Okay. All right. So now let's take a look at something that looks like this. 5 over x minus 1 minus 1 is equal to 12 over x squared minus 1. Okay. Now, it would probably be smart at this point here to factor everything. And the only thing that I can really factor here is this x squared minus 1. So this will become 5 over x minus 1 is equal to 12 over, and this will become x minus 1, x plus 1. Okay, so now I can see what my individual linear factors are for the denominator. I'm going to multiply through by my lowest common multiple there, which will end up being x minus 1. That is common because it's a factor down here. In that denominator, it's one of the factors. And then there's this leftover x plus 1. When I multiply that by the first term here, the x minus 1s will cancel, and I'm going to be left with 5 multiplied by x plus 1 minus, there is no denominator here, so I am getting everything, the full meal deal there. And then on the right hand side, well, both of those factors are in the denominator, so they would cancel. I'm just left with 12. Now, this is a very different expression, or equation I should say. And I have lost visually what my non-permissibles are, so I have to include that. X cannot be equal to, and I take it from here, plus or minus 1. Okay? Now, I've gotten rid of the rational sort of aspect of this. Now I'm just looking at a polynomial here. Let's solve this by expanding. So 5x plus 5 minus, okay, well this is a difference of squares. This would become x squared minus 1. I'm going to put the negative through, so negative x squared plus, plus 1 is equal to 12. Bearing in mind x can't equal plus or minus 1. Let's make that, actually I tell you what, because the x squared here is negative, let's just take everything over to the right hand side. So 0 is going to equal positive x squared minus 5x. Okay, well that became 6. 5 and 1 is 6, and when I brought it over it became negative 6. But with the 12 there, the result is positive 6, so x can't equal plus or minus 1. If we factor that, we're looking at factors of 6 that add to negative 5. Now, this is negative 6, sorry, positive 6 here, negative 5, so they're both the same sign. And, well, yeah, sorry, they're both the same sign here. They both have to be negative. So is it 6 and 1 or is it 2 and 3? And I'm looking at this and it's going to be 2 and 3 here. So when I solve the linear factors here, that would be 2 and that would be 3. The restriction here was that x couldn't equal plus or minus 1, and it didn't. So that's my answer. Now, had this been 6 and 1, you would have gotten an answer of 1 down here, but my restriction cancels that out, so I'm fine. That's my answer.
And finally, in this video, we're going to practice solving inequalities.
All right, now we're gonna go back and we're gonna focus more on expressing solutions to inequalities here. So, and this is going to become an important part of this course. And you'll see what I mean when we get there, that this idea of finding when a function is either positive or negative in general is significant in calculus. Let's just take a look at a really simple one here. 3x plus 7. Let's say I'm interested in where this is greater than 0. Okay? Now, to solve this one right here, there are a couple ways that you could do this. One way is to, because it's just a linear function here, it's just linear, there's just 3x plus 7, I could bring the constant term over, so 3x is greater than negative 7, and then I could divide by 3. So x is greater than negative 7/3, okay? And if we write that using interval notation, okay, because x is greater than negative 7/3, negative 7/3 is the far left side of that interval, and it goes out to positive infinity. And I use parentheses because we're not including that endpoint. That's one way of doing it. Another way of doing this, though, is to take a look at this guy right here, realize that it's a linear function, and let's just quickly identify its x-intercept. Now, some of you are fairly adept at this. You know right away, and we just did the work here, that that's going to be negative 7/3. It's a line with a positive slope, so it's going to look like this. And so when I ask the question, okay, where is this function greater than 0, bear in mind that this part right here, if I was to graph this, I would make this y equals that. Now the reason why that's significant, everybody, is because that is y. 3x plus 7 is y. It's equal to y. So I'm asking, where is y greater than 0? I'm not asking where is x greater than 0. I use the x coordinates to identify when y is greater than 0. And when my x value here is larger than negative 7/3, and what I mean by that, x is larger than negative 7/3, I mean, here's negative 7/3. X is larger means to the right of 7/3. The y coordinates of all those points are greater than 0. They're above the x-axis. Okay? Now, how else might this look when we get the question? Well, okay, they could split up the function maybe a little bit here, maybe make this 2x plus 1 is less than, and let's say less than or equal to 5x minus 11. Okay? Now, I will do this one a couple different ways as well. Let's say I bring everything over to the other side. So 2x minus 5x is negative 3x, and then maybe I add my 11 to both sides to get 12, whoops, less than or equal to 0. And you might do this so that basically this question looks very similar to the one that we just did, and then you can choose a couple of ways of working that through. Maybe bring the 12 back over, so negative 3x is less than or equal to negative 12, and then divide by that negative 3. And I'm choosing to do it this way right now so that we can talk about this. Now that I'm dividing by a negative, that will change the directions of the sign. We get x is greater than or equal to 4. And I would write that as, it's greater than or equal to 4. I'm doing that backwards here. 4 square brackets to imply greater than, and then because x is greater than that, I move to the right, and there's no limit there, so I'm just going to put a positive infinity, so 4 out to infinity. The other way I could have done this right from the beginning, though, is just get lazy and move that 2x over. So this becomes 1 is less than or equal to, and if I bring the 2x over, I'll get 3x over here minus 11. And I bring that over here so that this is positive, so that the x is positive right away, and then I might add the 11 to both sides to get 12, and then divide. And here again, although it's written differently, this is expressing that same relationship. X is still greater than or equal to 4. And in fact, the way that's written there, you can see quite clearly that 4 is the left-hand side of that interval, and then there is no right-hand side. So out to infinity. And these aren't even the only ways of doing it. Again, you could interpret that as a linear function, find its x-intercept, and so on and so forth. Okay, there's a few things you can do. Okay, let's take a look. Well, okay, what if we give you an expression that looks like this? And we're going to kind of build our way towards a problem here. What if I've got x minus 1 multiplied by x plus 4, and I want to know where this is less than 0. Not less than or equal to, just less than a 0. Okay, so I've got the product of two binomial factors here, less than 0. Here's how I would recommend you look at this thing here. The two individual factors here give me roots here of 1 and negative 4. Those are where this side becomes 0. So along my x-axis here, at negative 4 and at 1, that expression is equivalent to 0. Now, that's significant because if I want to know where this thing is greater than 0 or less than 0, I kind of need to know where 0 is. It's like knowing where the fence is. As long as I know where the fence is, I can tell you what side I'm on, right? But I got to know where that fence is. So here are the fences at negative 4 and positive 1 here. Now, if you were to expand this out, you would get a parabola, or if you were to graph this, you would get a parabola that opens up. Okay? I know that because what I can see right now, the leading coefficient here would become positive. Now, positive leading coefficient, parabola opens up. Remember, this represents the y-coordinate. So every point on this line, okay, generated by this function here, I'm interested in where its y-coordinates are less than 0. And that's going to occur in between these two. I can see it because here's the 0 line, okay, going along here. This is where I got to go down from that x-axis down here, in between negative 4 and 1. So as long as x is in between negative 4 and 1, these values here, the product of those two are going to be less than 0. Now, not including the negative 4 or the 1. And so if I write this in interval notation, that would be negative 4, positive 1, and I would use parentheses there because I'm not including the endpoints. Okay, let's do a similar problem to that one. And you'll see what I mean by that. X squared minus 7x plus 6 greater than 0. Now let's maybe say greater than or equal to. We'll kind of alternate here. If I give the question to you in this form, well, what do I want to do here? Well, okay, bear in mind, I want to solve it. I want to get that interval where these things are, that inequality is true. It was easy to do when it was in factored form. Oh, so I should probably factor that. So x and x, and now I'm looking for factors of 6, positive 6, whose sum is going to be negative 7, and that will be negative 1, negative 6. So now, when I take a look at this, if I was to graph that, I can tell you right now my x-intercepts here will be at positive 1, positive 6. Same as before, this is going to give me a parabola. Okay, it's quadratic that opens up. I know it opens up because the leading coefficient is going to be positive. Now, if it wasn't positive, I would move everything over to the other side of the equation so that it was positive. Okay, I like these things better when they open up. It's not going to change the answer, just make it easier for me to work with. I want to know where this parabola is greater than 0, where the y-coordinates are greater than 0. Okay, not the x-coordinates. I want to know what x-coordinates produce positive or 0 y-coordinates. Now, 1 and 6 both produce 0, so I'm interested in those. Now, from 1, do I have to go left or right to get positive numbers? The answer is to the left. So if I choose x values that are less than or equal to 1, or x values that are greater than or equal to 6, because again, look at 6. 6 produces a 0. I want 6. Sorry, I want that to occur. I want the 6 value to show up in here, but do I want to go to the right or to the left? And the answer in this case is to the right. Now, in interval notation, that would look like this. Negative infinity, up to 1 and including 1. And again, I put square brackets there to indicate including. With infinities, you would only ever use parentheses because you never actually include the infinity. Infinity is not a real number. And then because I want this to look cool, I would put that union symbol. Okay, that means together with, and then over here, my answer would look like that to indicate that I'm starting at 6. 6 is the low bound of this interval, include it, and then I go up to infinity. Okay, good. Let's do a little bit more here. F. Okay. I've got one here a little bit more complicated, but it's in factored form. We'll start off with it like this. Okay, let's just say I'm looking for where this particular function is less than or equal to 0. Now it's in factored form already. It's a polynomial. Okay, so I'm going to yank out of this what its roots are, and its roots are going to be positive 4, positive 1, and negative 2. Let's just draw that out. So here in order, negative 2, positive 1, positive 4. I don't really care about the scale, just so long as they're in the right order. Okay, this has got a degree of 2, linear. So all together, when I multiply that all out, I'm going to get a quartic. I'm going to get a quartic that opens up because there's no reason for the largest degree term here to be negative here. There's nothing that multiplied by the x here to make it negative. So it's going to open up. The negative 2 has a multiplicity of 1. So does the 1. So the graph's going to drop down, come back up. And then the 4 has a multiplicity of 2. So the graph is going to look like this. It's going to be tangent to the x-axis at 4. Now the question I'm asking here is, where is this function less than or equal to 0? Well, it's equal to 0 at negative 2, at 1, at 4. So I'm going to include those numbers. That's fair. And then where is it less than 0? Where does this graph drop below that line? And the answer is in between negative 2 and 1. And so that's how I answer my question. In between negative 2 and 1, if I choose any x value in between those two, the resulting y coordinate will be negative, together with x equal 4. Okay? Because all on its own here, that number there produces a 0, and I am including that. So in interval notation, I might write negative 2, 1, and the square brackets indicating I'm including both of those, and then I put the number 4 out there. Okay? Not in interval notation, just the number 4, all by itself. Okay? Actually, that's a good question because of the way that was written there, including that little number there, because you do want to include places where that goes to 0 when it's the only one. Okay, let's just do a handful more here. Let's grab, I don't know, let's say we start with x squared less than 3x. Okay, now for me to analyze this right here, it's a quadratic because I see the square here, so I want to compare everything to 0, so I would bring that over first. Very simple here, I would just factor this. So x multiplied by x minus 3 less than 0. Now, okay, now I need to consider this sort of graphically here. So take a quick look. I've got x and x minus 3. That tells me that my roots are going to be 0 and positive 3. Oftentimes the mistake made here, and the reason why we want to look at that, is when the x is by itself, a lot of times it gets forgotten. Okay, but it does produce a root of 0. It's a parabola that opens up, so the parabola would look like that. Again, I'm interested in where this thing is less than 0, okay, not equal to 0, just less than 0. That means below the line. And so in this case, that's going to be between, when x is between 0 and 3, the y coordinate. So when I point in between 0 and 3, the y coordinate is below the line. I got to drop it down here. And in interval notation, I would write that as 0 to 3. Okay, there you go. What if I've got something that looks, I don't know, let's try it like this. X squared less than or equal to 5. Okay. Now I would be very tempted to do it this way. Bring that 5 over so it's equal to 0. It's just in my head that it's a pattern that I've already established. I mean, there is another way I could go about doing that, but this is a pattern that I've already established. It works. Let's just keep with it. Now, but this requires that I factor this. it doesn't factor nicely, but that's okay. Whoops. I can force that. And I'm going to get here that my roots are going to occur at negative root 5 and positive root 5. Again, it's a parabola that opens up. I'm interested in where this thing is less than or equal to 0. I tell you what, let's even change the question here. Let's make this a little bit more. Let's look at where it's greater than or equal to 0. Let's just change this like that. Greater than or equal to 0. Just so it's opposite the one that we just did. Oops, sorry. Oops. Now, I want to know where this thing is equal to 0. Well, that occurs at those 2 points right there. And then greater than 0. So cover that up, cover up the underneath here. I want to know where it's above. And that's going to be back here when x is less than or equal to negative root 5, or x is greater than or equal to positive root 5. And then in interval notation, that will be negative infinity up to and including negative root 5, together with positive root 5 out to infinity. Okay? See, I love this stuff. All right, a couple more. Let's go back and take a quick look at whoops, E, F, G, H. Oh, sorry, I meant I now. Just a couple more. X plus 1, 2x plus 1, x minus 6. And I'm interested in where this is greater than 0. Again, this is in factored form. It's a polynomial. I would simply take use of the fact that you should already know, like this is degree 1, degree 1, degree 1. So this is in the form of a cubic. The roots here are going to occur at negative 1, negative 1/2, and positive 6. Okay, if I get a sense of what this thing looks like, then I can sketch it really quickly, and then I can tell you where it's going to be greater than 0. It's a cubic with a positive leading coefficient. So this thing's going to go up, multiplicity of 1, down, multiplicity of 1, and then back up, multiplicity of 1. I'm interested in where this function is larger than 0. Now it's equal to 0 at those numbers. So it's larger than 0 here and larger than 0 here. So that's going to be in between negative 1 and negative 1/2. And then greater than 6. And in interval notation, that will be negative 1, negative 1/2, union, and then 6 out to infinity. Okay, and maybe one more here, really just to highlight the multiplicities here. Now, if you get an expression that's not factored, then that's your first goal. Okay, and normally when I go through this, that's one of the things that we would do is we would do a question or two where we have to factor first. But the truth is we've done a lot of, if you've followed the lessons through, we've done a lot of factoring. Okay, so we're going to assume right now that that's not the issue. The issue right now is interpretation. So here when I look at this, it's a polynomial, everything's over on one side, I'm comparing it to 0. I see that my x-intercepts here are going to be at negative 4, negative 1, positive 3. This is degree 2, degree 1, degree 1, so this is a quartic. The way it's set up here, it's a quartic that opens up. It's because it's got a positive leading coefficient. The multiplicity of the negative 4 is 1, so it's going to come down. The multiplicity of the 1 here, the negative 1 is 2, so it's going to bounce off. And then the multiplicity of the 3 is 1, so it's going to look like this. So where is this function greater than or equal to 0? Well, it's equal to 0 at negative 4, negative 1, and 3. It's greater than 0 to the left of negative 4 and to the right of 3. So when x is less than or equal to negative 4, don't forget about the negative 1. And then when x is greater than or equal to 3. Now, I've got the two intervals here in a single number. Don't forget about the single number here. If it was just greater than 0, then you wouldn't have included that, and then you would have dropped the or equal to here. Okay? If that was what the question was. But it wasn't. So in interval notation, this will be negative infinity up to negative 4 and including, union negative 1, union starting at 3 and heading out to infinity. Okay. All right, that's enough with questions like that. When we come back in another lesson here, we're going to look at a similar sort of question, but with rational expressions, not polynomial expressions. And we're going to look at solving inequalities in that context.